Lesson 1.4 Prime Factorization. In this lesson, you will use divisibility rules to determine the prime factorizations of numbers. Because 2 is a factor of 10, and 2 times 5 equals 10, 5 is also a factor of 10. The pair 2, 5 is called a factor pair of 10. Example 1, finding factor pairs. The brass section of a marching band has 30 members. The band director arranges the brass section in rows. Each row has the same number of members. How many possible arrangements are there? Use the factor pairs of 30 to find the number of arrangements. Factor pairs of 30, I could have 1 times 30, or 30 times 1. So I could have 1 row of 30, or 30 rows of 1. I could have 2 times 15, 2 rows of 15, or 15 rows of 2 each. 3 rows of 10 would equal 30, or 10 rows with 3 each. 4 is not a factor of 30, but 5 is. I could have 5 rows of 6, or 6 rows of 5. And then I'm to 6, which I've already done, so I know those are the only possible combinations I could have. That would be 1, 2, 3, 4, 5, 6, 7, 8 possible arrangements for 30 with the same number in each row. Key idea for the prime factorization. The prime factorization of a composite number is the number written as a product of its prime factors. You can use factor pairs and a factor tree to help find the prime factorization of a number. The factor tree is complete when only prime factors appear in the product. A factor tree of 60 is shown. So I'm starting with the number 60, and I've broken that down into 2 times 30. 2 is prime, so it's circled. Then I need to break down the 30 into 2 times 15. 2 is again prime, so it's circled, and I have 15 left. 15 has been broken down into 3 times 5, which are both prime numbers. So the prime factorization of 60 is the product of those 4 numbers, 2 times 2 times 3 times 5. And since I had 2 of the 2's, I could write that as an exponent as 2 squared times 3 times 5. Divisibility rules will help you with determining whether a number is divisible by another number or not. For example, a number is divisible by 2 if the last digit is even. In the column over here that says it's divisible, 3,978 has an 8 in the last digit. 8 is an even number, so 3,978 is divisible by 2. In contrast, 4,975 has a 5 as its last digit. 5 is not an even number, so that whole number, 4,975, is not divisible by 2. A number is divisible by 3 if the sum of the digits is divisible by 3. Sum means add, so 3 plus 1 plus 5 equals 9. 9 is divisible by 3, so 315 is also divisible by 3. 1 plus 3 plus 9 is 13. 13 is not divisible by 3, so neither is 139. A number is divisible by 4 if the last 2 digits form a number divisible by 4. So the last 2 digits in this one would be 12. 12 is divisible by 4, so is 8,512. 18 is not divisible by 4, so neither is 7,518. A number is divisible by 5 if the last digit is a 0 or a 5. That's an easy one, you just need to look at the digit. A number is divisible by both 2 and 3, then it is divisible by 6. 48 is divisible by 2 because it has its last digit is an even number. It is divisible by 3 because of the sum of those two numbers is 12, which is also divisible by 3. That means it is divisible by 6. In contrast, the 20 is divisible by 2 because it ends with 0, which is an even number. However, it is not divisible by 3 because 2 plus 0 is 2, and 2 is not divisible by 3. A number is divisible by 9 if the sum of the digits is divisible by 9. Again, the sum of the digits, 7 plus 1 plus 1 is 9. 9 is divisible by 9. But 9 plus 3 is 12, and 12 is not divisible by 9. So 93 is not divisible by 9. And a number is divisible by 10 if the last digit is 0. Again, like the 5, it's easy. Just look for a 0 in the ones place. This one has it. This 10,536 does not. Example 2, writing a prime factorization. Write the prime factorization for 48. Well, since I just talked about my divisibility rules and I see an even number in my ones place, I know that 2 is a factor of 48, so I will do 2 times 24, and 2 is prime. So I need to break the 24 down because I know that's a composite number, and I know that 2 times 12 is 24. Again, I know it's a factor of 2, 2 is a factor of 24 because of that even number there. And again, I see an even number, so I know 2 is a factor again. 2 times 6 is 12. And I can break 6 down into 2 times 3. And now I have all prime numbers, so I can rewrite my prime factorization now as 2 times 2 times 2 times 2 times 3. And if I wanted to write my 2's all together as a power, I would have a base of 2, and I have 4 of those times 3. And just to show you that I could do this prime factorization, again, starting with different numbers, and you will arrive at the same answer as long as you are accurate in your division. Let's try 6 and 8. 6 times 8 is 48, and we know that is a basic fact. 6 I could break down into 2 times 3, which are both prime numbers. And the 8 I could break down into 2 times 4. The 2 is prime, but I would need to break the 4 down again into 2 times 2. Now I have all prime numbers. Rewriting my factorization, I would have 2 times 3 times 2 times 2 times 2. And if I combined all my 2's into a power again, I would have 2 as my base, and 1, 2, 3, 4 2's, so 4 is my exponent times 3. And my answers match. Example 3, using a prime factorization. What is the greatest perfect square that is a factor of 1575? Remember back from lesson 1.2, the square of a whole number is a perfect square. So what we're really being asked is, what is the greatest whole number that we can square that is a factor of 1575? In order to figure this out, because 1575 has so many factors, it wouldn't be efficient to list all of the factors and check for perfect squares. Let's do a prime factorization and find any perfect squares that might be factors. Starting with 1575, I see a 5 in the ones place, so I know that it is divisible by 5. So I will start there. 5 is prime, and 5 goes into 1575 315 times. And I see a 5 again, so I know it's divisible by 5 again, so I will do that. 5 goes into 315 63 times. And then 63 looks familiar now, is 7 times 9. That's a basic fact. 7 is prime, but 9 is still composite. I can break that down into 3 times 3, and those are both prime now. So there's my prime factorization. When I rewrite that, it would be 3 times 3 times 7 times 5 times 5. It's very clear right away that we have a 3 times 3, so that would be a perfect square. We have a 5 times 5, so that would be a perfect square. But there's one tricky part that we could play here. Since we have 2 numbers of each, we could partner them together and make those be 15 times 15. 15 times 15 would be the greatest perfect square that is a factor of 1575.